Welcome. Welcome to 5G Era Workshop. This workshop is designed to demonstrate 5G Era's latest progress, focusing on transformation from cloud robotics to 5G, 6G-enabled connected robotics. We are planning to present the technologies developed, as well as we will provide a live demo with one of our robots. You can see it here. Before we proceed, please let me thank OTE Academy for hosting this event in their beautiful venue. So we can now start. Thanks, please.
Thank you very much, Christina. Thank you very much for everyone coming here today. My name is Renxi Qiu. I'm a professor in University of Bedfordshire. I'm also the scientific coordinator for the 5G Enhanced Robot Autonomy Project. For this one, this workshop, we are trying to demonstrate our effort to transform the application of cloud robotics to the future of 5G and 6G enabled connected robotics. Robotics is always a hot topic for general audience, and there are lots of potential capabilities, potential applications. Although this is also a field we normally see things like after 10 years, we're still talking about similar stuff. Cloud robotics is one of hot topic for robots lasting for already 1 or 2 decades. Robots need to do more intelligent things, and robots need to be more capable. So in that sense, we want to offload some of the tasks running in the robot to be running in the cloud, to be running in the edge, and eventually we hope we can deliver better robots to serve people and to serve the community. But I would say that this is still on paper because you can see a lot of effort in translating the daily activity into robotic service, into cloud robotics. However, we face quite a few issues in actual accepting the application by the industry, although there are lots of effort like Amazon providing the cloud robot service like Robot Maker. But majority of things we face in the robot application, especially related to the networking, is that the applications are normally designed for structured and industrial environment. In this sense, you have fixed quality of service, the network topology is generally static, and you're working in single domain, single administration environment. Unfortunately, this is not the case we have with our internet, and we normally face different kind of challenge in terms of unstructured network, in terms of topology, different administration, etc. As a result, a lot of appealing application for robotics is not actually translated to our services in the community. Example I give you over here, this is a ROS called Robot Operating System, which is one of the de facto standard utilized by robot industry. Some of the limitation you can see that for ROS 1 is largely working for a single domain, single network, and for ROS 2 they use multicast and unicast. Most of the time they don't work unless you have VPN enabled. So we want to get the help from networking community, and we want to use your wisdoms and to improve the deployment of the robot, and lots of potential things we could do. We want to have the whole world, digital world, to be orchestrated to help us to improve the quality of experience for robot. To achieve that, there's always something, if you come from networking background, you will see. You want scalability. You can't just deliver your solution for a single application. You want the solution, especially from teleoperator's perspective, to be scalable, working for all different kinds of situations. They need also big transparency, so you could have, you know what is happening inside. So in essence, this is a kind of not in the same direction as we are hoping for cloud robots to be personalized for our robot application. And this has come through the 5G Era project, 5G Enhanced Robot Autonomy. What we want is that we want the robot to be clever enough to utilize the digital infrastructure from the environment to maximize the quality of experience together with the orchestrator generated from the networking community. We started in 2021, and this is our third year. We'll be finishing the project next year. What we achieved so far is we improving the 5G or 6G experimental environment specifically for robots. You will see from the presentation today, you can see a different way we're trying to enhance the experimental environment for robots by building up this so-called connected robots is a step forward to the cloud robot. And what we are doing here is that we're trying to extending the concept of network softwareization and virtualization fully into the robot. So in that sense, the developer for robots could share same concept, could share same terminology with the networking community. We hope we can have better outcomes by working together. And then what we implemented is a connected robotic platform. We do the software-controlled instantiation of the virtual networks according to the demand from the robot, according to the vertical demand, to maximize the experience of our robot. So this is what we delivered as part of so-called Connected Robotics Platform Corp. And we built an ecosystem for robot development. They are still in the same language of general robot developer, but we share a lot of concept from the networking community in the robot development. Eventually, we enable 5G enhanced cloud robotics to adapt themselves, become connected under the network and connected intelligence. So a different kind of advantage we are claiming. You will see that from my colleague today. They will demonstrate how do we deliver the potential benefit, truly benefit the networking capability in the robot development. We will show you a few use cases first. My colleague will talk about the PPDR and logistic robots, semi-autonomous robots, and manufacturing applications. And then using these use cases, we will show the benefit of the connected robots. We take advantage of cloud resources, we take advantage of edge computing, but more importantly, we take advantage of the whole network behind us to deliver better robotic service. So that's the agenda for today, and you can see that we will start with the use case, 3 of them used by the project, and after that, we'll talk about what is behind those use cases, because you can see lots of people talking about use cases for 5G, for 6G, and in our sense, we trying to fully implement the network softwareization for the robotics. We will explain how do we achieve them by the technical issues we're explaining. And in the afternoon, we will have 4 booth sessions in this room showing our use cases and reference design. And finally, we will have our seminar and the tutorials together with the booth sessions explaining about our fleet management ideas, and tutorial on how to add security and identity management, how to use the relay network. We mentioned that. We want to do the full softwareization for the robot application. So this is behind the implementation. They are available on GitHub. We'll do the tutorial with you. And then finally, we have our live demo of a simulated PPDR robot in the car park of OK Academy. Thank you very much for everyone come here and to see what we do. Looking forward to see your suggestion and your interpretation on our effort to bring the networking community and the robot community together for the future of connected robotics. Thank you very much. And I will move to our first use case. And the use case is about different kind of robotic application, mainly for PPDR and for the PPDR and also for the logistic robot. And Guilherme from Robotic Automation of Spain will do the presentation for us. Let me see which one is your presentation.
Maybe it's I don't know.
So we will have 3 use cases of robot application to be presented to you, and one of them is about logistics and PPDR. One of them is from Rihalto. This is about semi-autonomous transport robot, and then the other one from the UK from TWI and Power Robotics. We'll talk about manufacturing robot, and yeah, this is the first one.
Hello everyone, my name is Guillem Garia. I am an R&D engineer from Robotic Automation. I'm going to present the 2 use cases. One is the public disaster relief and the healthcare thing with mobile robotics, and how 5G era can enable to achieve better performance with this. So first is to check the use case and the network applications. So first, the PDDR or the surveillance case. We are having this robot, and the idea is to, in case of disaster, like Renchi said before, that this is an unstructured environment. The idea is to make a different kind of mapping, and also in order to get recognition for, in case for searching person, to evaluate damage and this kind of evaluation in case of disaster. And with that, we propose to use our robot always is limited by the capabilities that they have. So the idea is with 5G era is to offload some of the high consumption processes to an edge or a cloud. So one of the first one is the frontier exploration, is one of the network that the applications that will allows us to make a whole map of an unknown area. Using that, we have the SLAM. SLAM is simultaneous location and mapping. And the idea is to make this kind of topological map in order that the robot can orientate itself. And also we have the human presence that we use AI, that is something that is, the computing processing is heavy, in order to detect persons in case that if it's an earthquake or a disaster, in order to automatically detect some people in case that, and point the location in order to make the rescuers easy the work. And also we need a teleoperation, because sometimes the automated way of navigation the robot is not enough, and you want to go to specific places, and we wanted this teleoperation to offload it to the edge or the cloud. In the logistic use case of the healthcare, we have like a hospital or a logistic, but if we can take account of the hospital, we see that the hospitals are very variable. So this is not like the traditional warehouse when everything is fixed. So this is when the kind of unstructured environment comes with the 5G era. So the idea is more or less we have the teleoperation because we want to move things from point A to B. But sometimes you need to know, sometimes you need to release the automatic control to the operator. Also, we need a map, this kind of robotic map, the SLAM. And we have 2 other things that are quite interesting. This is the signal quality mapping that is very interesting for the networks enterprises, that will give us a map of how well the 5G network is deployed in each point. Also, because we could have more than one robot, usually in the logistic case, we need some kind of fleet management that commands how to go to point A to point B inside the map. So let's go to the use cases application. First, we have this. This is we have delivered these use case applications that, for example, this is the operation, the SLAM, the fleet management, the frontier exploration, and the human presence and the signal quality. So let's start with the teleoperation. Teleoperation is what you expect, is to try to control the robot from a remote location. The idea is like if some operator can control the robot with a high uplink, with using the benefits of the 5G, that we can have a slice when we can go with high upload throughput and low latency in order to have the less delay in order to control in the fastest way. So next is the SLAM application. SLAM means, as I said, simultaneous location and mapping, is to locate the robot and make the map on the same time. This is a very CPU-intensive process that almost can outrun the capabilities of the local robot. So this application can give us much more room if we do it on the edge or the cloud, because even though we can have higher capabilities, even can get greater precision with this. This is the kind of map that the robot produces. This is more or less that the robot understands. And the idea is to offload this to something that is power corded and it has higher capabilities. The next one is a fleet management application. This is a pure robotic application. This is the application that tells the robot where to go and which is the intermediate points, and tries to resolve some kind of conflicts, because if you have a shared lane, and we have here in the middle alley, there is only one robot can go there. So if the robots face each other, this software can solve this kind of conflicts in a way that minimize the energy and maximize productivity. So with 5G, with the 5G era, what we wanted to do is like a smart placing of this, because usually this is fixed. But what we wanted to do is this thing that usually comes to the edge comes dynamically or fluidly on the cloud or the edge, and 5G era decides where our software decides where to place it without the user doesn't decide it. So this is a great advantage for the robotic community. So we have the frontier exploration. I was said this is like a joint application that when you have an unknown environment, you will need to make a map of the robot in order to locate itself, and also you have the 3D map. And also you will need some kind of 5G quality signal also, because if you wanted to do some things like offloading or human recognition, you will need to know where is forbidden to go there or not, or is this a bad choice. So, and also we combine it with remote operation, because if we have something that is more industrial-like, will be easier to make some kind of algorithm that sweeps the area. But with this kind of unstructured environments, we need something that rely on a human in order to have a good map of that. So let's move to the human presence. This is an application for detecting people. We are thinking that in case of disaster, the idea is like you use the AI recognition that for this kind of robots is kind of heavy load and can stress a little bit the computer inside. The idea is to detect a human, like these examples, and save the location of the robot on that time. So afterwards, or maybe to send rescuers to that location. So this is the idea that maybe when the robot is doing the map or when sweeping to search for area, automatically detect people and send this location to the rescuers. The signal quality application is I was saying, this is to make a map of the signal quality of the 5G. So the idea is, I think this is a very interesting application for the network community, because usually when you are deploying antennas or this kind of environment, you need to know you have black spots or something that you don't have good signal. With this, we make like a semantic map that this is like a color map that we indicate how well the signal arrives to the robot. Even though with this we can make an application that instead of measuring the quality with a human person with a backpack, we can use the robot, and also it will be better for the robotic community because usually the antennas are in a lower position than usually when the people have it in the backpack. So I think this is a very good, a great idea for the network, enterprises in order to make this kind of deployment even better. You know, for example, on that area that we have low signal. So if we want to deploy something homogeneous, you should put another RAN or another infrastructure over there. So let's see what we have what we have done in the last few months. So we were here. Thank you for OTE to having us, and we could make this map with the signal quality, and also we test the surveillance outside with the with the human presence application, and we have the PDDR. I don't know if this. So we have some kind of video that I hope it. Well, my Greek is not this. I think this goes here. Okay. So this is a video with the surveillance case. So more or less, this is the way of what is the workflow. So the first sweeps the area and as the exploration mode in the frontier exploration, and you can see this is a robot for outdoors. So we should expect changes, and it will sweep this. For example, this unstructured area. And now it's like moving, making the map. And the map is not generated inside the robot, it's outside. And also it's like searching for people. Now the robot returns to the base. Now he has make a map of the area, and now he can move more precise to certain areas. So now he has the map, and he can start the second phase. Now the second phase is once we have the map, the robot goes to the NAS location in order to check if now a remote operator can give a control so it can come closer to the robot, to the person, and also it's located itself with the map, with the previously mapped generation. Also, this map could be shared among other robots if we have more. So this is like a great advantage to have it on the edge on the cloud. So now it's returning to the last known presence, and and it provides the robot can navigate autonomously to the human point. And now it's like giving giving remote control to the operator. So I think that's it. And thank you for your attention.
Thank you very much.
If you have any questions.
Maybe we can have questions together.
Maybe.
Natas will show us the second use cases on semi-autonomous robots.
All right. Good morning, everyone. My name is Mateusz Kaszuba from the Bring Out company, which is a Czech technological startup or company working in robotics area, robotics segment. I'll try to introduce to our use case, which is the industrial one, the logistics one. I'll try to show you the outcomes of the 5Jira project within our use case. We've been working on the use case mainly with BUT, which is a Czech University Faculty of Information Technology, and Cognitecna, which is a spin-off from the university, and also, of course, the other partners. So briefly about the use case, the robot we are using is obviously not here physically, unfortunately, because it's quite a big one. It's a robot of a passenger car size, so 3 meters long, 1.5 meter wide, 1 ton heavy. So in this case, it's a pretty big robot. It's an autonomous robot used mainly in the industrial sector. So its main usage is for cargo transportation within production plants, within the outdoor intralogistics of production plants. It's a four-wheel chassis, either two-wheel drive or four-wheel drive, powered by electricity, operating outdoors, so it means in snow, in rain, in wind, and all possible weather conditions. What we do use is drive-by-wire technology. We have a LiDAR-based and GPS-corrected autonomous driving. We have a camera-based teleoperation system. And as I've mentioned, the weight of the robot is 900 kilos. The payload is another 700 kilos. The maximum construction speed is 40 kilometers per hour, but autonomously we drive 20 kilometers per hour. And the range of such a robot is 70 to 80 kilometers per one charge. What are the challenges within this use case is that the robot is intended to operate in industrial areas, which means that it is not only outdoors, but there is also some traffic, which is often mixed, consisting of pedestrians, cyclists, motorcyclists, passenger cars, heavy and light-duty cars, lorries, trucks, forklifts, of course, trains, etc. And thus the environment is pretty much complex and unstructured, like Renxi mentioned. This is the main challenge. And in this case, you need not only the navigation of the robot, the autonomous navigation, but also you need to detect the obstacles on the route. You need to avoid collisions in order to deliver a safe operation of such a robot. As it's pretty heavy and there is a braking distance, then you can't afford to collide with anything in this case. Another challenge we are trying to solve within 5GRA is, of course, the offloading, and it's regarding not only the battery savings, but also the computing power savings. So we are trying to offload some tasks from the robot to the cloud. I will talk about it in a moment. This is how the robot looks like, and we can move on to the outcomes we are trying to reach within 5GRA. The two main ones are two network applications. I will talk about them in a while. The first one is train sensor, and the second one is collision avoidance. Regarding other hardware and software which we use within 5GRA, there are three automotive-grade cameras used for these tasks and for these network applications with 120 degrees field of view. Then there are clients running on Jetsons, which are communicating via public 5G networks using the router RouteX50 for the communication, and the communication with middleware, with 5GRA middleware, which is deployed in the cloud, as well as the network applications, which are deployed in the cloud. But the network applications are also deployed locally. That's because when there is an area where the network performance is pretty much poor, then we need to seamlessly transfer from cloud processing to local processing to enhance the performance of the network in that case. But the main outcome is that we are able to offload it to the cloud, so the local processing is used just for a backup if the network is poor. Let's now take a deeper look in the network applications we are developing. So the first one is train sensor. The question now is, why would we even need something like a train sensor? There are two main types of production plants where we deploy our robots. And those are heavy industrial production plants where the cargo is heavy and it needs to be transported by train. And the other ones are larger, like historical or traditional industrial areas, which were built in the past. And in the past, the trains used to be used for cargo transportation mostly. So that's why the trains are present there. In most places, the trains are crossing the road in various directions. And the challenge here is that sometimes they are approaching the crossing with the road from the blind spot direction of the robot. So that's why we need to detect them, and we need to make sure that the robot is safe to cross the crossing without colliding with the train. So this is just an example how it can look like. And the workflow of this network application is pretty much straightforward. As I've mentioned, we are using, in this case, two cameras, the front right and front left on the other side of the robot. So those are two cameras used for this network application. The workflow is like the robot comes to the railway crossing, it stops in front of that crossing, it triggers the detection of trains and detects the trains for how much time is needed to be 100% sure that the crossing is safe to pass. The results we obtain after processing within the network application are four main ones. Those are that there is no train detected at all, or there are some trains detected, but they are not moving. In that case, it's safe. The third one is that the trains are detected and they are moving in either direction. And the fourth one, which is a bit of issue sometimes, that the detector, the YOLO5 detector, is not able to detect and determine whether it is a train, whether it is moving or not, and so on. In case the trains are not detected there, or they are detected but not moving, for example, 7 seconds, we can set this value. Then it is a signal for the robot, for the autonomy system, that the crossing is safe to be crossed and passed. This is how the train sensor works. The main or the important thing here is that the train sensor network application is not running all the time. It is rather triggered only on the railway crossings. And that means that we are able to offload even more, and we are able to save the power by triggering the network applications only when there's the crossing, not all the time. Now this is a video of how it looks like. So you can see my colleague Aladdin riding the robot there. The robot is moving autonomously on a pre-mapped route. Now it comes to the railway crossing. So it stops in front of the crossing and it triggers the detection. Now down there will be the views of left camera and right camera. So as you can see on the left camera, for example, there is a train detected not moving. On the right side, there is a train, it's moving, and it's detected in this case. And there are also trains behind the blue one. So the robot waits for now, as it can detect the trains which are not moving, and that means that it's safe to pass. But there was the blue train which was moving, and this was the signal for the robot to wait, and to wait till the train passes in order to be able to cross that crossing. So now the train is on the left there behind. It slowly brakes and stops moving. So the robot detects all trains as not moving, and this is the signal that the robot is capable of crossing that crossing safely. Now it continues in its mission, in its task, and it safely crosses the crossing. So this is how the train sensor network application works, and why it is important for us to sense and detect all the trains. Yeah. Nope. Okay. All right. Now we can move to the other network application, which is a collision avoidance. In this case, the way how the network application works is again pretty much simple or straightforward. The network application waits for the camera streams to be received. Then it detects the objects of defined classes in the image stream. It detects pedestrians, it detects cyclists, cars, etc. It projects the objects and predicts the path of the objects, which is essential. In this case, there are three main signals generated. Basically, it's four. The first one is that it's no signal generated, and it means that there is no object detected, or the detected objects are not about to enter any of the robot zones. There are two main robot zones, which is the red one around the robot, around the vehicle, which is called the danger zone. And then in front of the robot, in direction of the robot moving, there's a caution zone, which is the yellow one. Again, we are able to set the dimensions of the caution zone regarding the actual speed of the robot, of the complexity of the path of the route, of the part of the route, and so on. So the first signal is caution. It's in case on the first picture when the object is about to enter the caution zone, which is in front of the robot. The second signal generated is warning. It means that the object is already somewhere in the caution zone. And the third one is that the object is about to collide, so it will enter or enters already the danger zone. Of course, this case should ideally never happen, because it means that there is a time to collision, and it's pretty much possible that the robot and the object will collide. So this is just the brief idea behind these network applications. The visualization or the UI looks like this. in the top part there are the generated signals: caution, warning, danger. In the bottom left corner, there is the visualization of the robot space with the caution zone in front of it, and the detected objects marked with the red arrow and the green square. So this is how it looks like in principle. Why this is so important for us? Of course, whatever the robot, whatever the area, the environment, and whatever the use case, when driving autonomously in certain speeds, the collision detection or the obstacle detection and the collision avoidance are two systems which are essential for safe autonomous operation. So each autonomous robot should have these two systems to be able to navigate through the area and avoid any collisions. So this is why we need to detect the objects, why we need to avoid the collisions, and the workflow is a little bit different in this case. The collision avoidance network application runs the whole time, so it's a real-time object detection and tracking, not unlike the train sensor which is triggered, but rather the collision avoidance runs the whole time of the robot operation. As long as there is no object detected or the objects detected are not about to enter the caution zone of the robot drives at full speed, so let's say 20 kilometers per hour. If the object is about to enter the caution zone, it's the caution signal generated, and it means that the robot will slow down to half of its full speed, so 10 kilometers per hour in this case. And in case there is the warning signal generated, it means that the object is already in the caution zone, and the robot starts to brake and stop. In case there would be an object entering the danger zone, which ideally should never happen, the robot starts to perform emergency braking, but this situation should never occur. As soon as the robot stops, it waits until it is cleared to continue in its path. So it means in case no signal is generated or the caution signal is generated, for the robot to be able to move on and not collide with the objects. For this reason, or for this purpose, we use the front camera of the robot. And again, this is a video of how the collision avoidance network application works. So you can see cars detected from the image, and now it slows down because the car was in the caution zone. It turns down there. You can see the detected objects and the zone, the caution zone of the robot. It detects the cars, but there is another of my colleagues. The robot detects him. First, it slows down to half of its speed because there was the caution signal generated. And then, as my colleague stood right in front of the robot, it meant for the robot that it's the warning signal generated, and the robot stopped in that case. So this is just a brief showcase how it works. And we'll have in the afternoon session, the booth session, a live demo of how the collision avoidance works. It will be remotely done, so the robot is currently in Brno, in the Czech Republic, but I will be able to show it to remotely live how the collision avoidance works. This is all from my side, from our use case. I'm eager to answer the questions afterwards or at the booth session. Thank you.
Thank you very much. And it's a very exciting application for transport robot. And if you've got any questions, feel free to ask later or in the booth session. We also have a Q&A session after we finish explaining how we deliver this kind of capability. Our next use case is about the manufacturing robot and how we utilize the capability to deliver the potential manufacturing as a service for the future applications. And you go ahead. Better you copy them to the
back to your presentation. And then in Athens workshop.
Copy them to the desktop.
Yeah.
The presenters come from TWI. It's a well-being company. It's quite diverse research institute working on different manufacturing applications. And also Paul from How Robotics, they're building manufacturing robot control software. So they're building the framework for different kinds of microservices and robot applications. Go ahead, please.
Just 1 second while it transfers over.
Morning, everyone.
Right, good morning. So I'm Kandap Amin from TWI, and we're a research and technology organization. And Paul?
And I'm Paul McCard from How Robotics. We're a robotics software company primarily for the manufacturing and construction industries.
So we'll be talking about the manufacturing use case that we've developed for the 5G Era project today. So what we have is 3 steps in this kind of manufacturing process. We've got the pre-process steps, which essentially what it requires is loading of parts into our robotic cell, where the operator engages with the robot through either mixed reality or virtual reality to then engage and execute robotic movements through that. So the robot then assists the operator by conducting defect detection through a laser scanner, but also being able to dispense paste, which is essential for the process. So once that's all done, it's loaded into the furnace like you're seeing in the middle. And inside the furnace, the temperature is increased up to a high, for example, 1,000 degrees, where the paste is then melted, and then the temperature reduces where it solidifies and creates a component. Once this whole process is complete, the parts are removed from the furnace and then goes back into the post-processing step, which is on the right-hand side. And here what happens is the robot then assesses the part that's been manufactured and assesses it for defects and reports back to the operator. And then the cycle continues with the next part.
Yeah, so as Kandap's just been describing, this is obviously a very high expertise procedure to run. It's a process that requires a huge amount of training to be able to do properly as a human operator. So for us, it was critical to, at a very early stage of the project, break down all the stages that the cell was going to have to be able to deliver. So a big exercise for us at the beginning was building this sort of flow chart, this roadmap of what, at every stage the robot was going to have to take action on a part, every stage in which the operator was going to have to interact, whether that was through, as we're saying, VR or a mixed reality headset. And then that allowed us to break down the entire process into a set of microservices, which each is responsible for one part of this process. So, for example, we have a microservice that's entirely dedicated to handling jobs as they come in. So everything about the robot's operation, the part that it's operating on, is all handled by a single operation. Everything that interacts with we've got obstacle detection and human presence detection. The robot's capable of autonomously calibrating itself, and then running each individual part of the actual brazing operation is each handled independently. And what that allows us to do, especially with the power of the 5G Era middleware, is to deploy some of these applications where they need to be at the edge, next to, adjacent to the robot itself, or to the laser scan profiler, or the mixed reality headset. Those translation layers those applications all need to be at the edge in order to interact directly with the hardware. But also, similar to what Guillaume had said before about in their deployment, we can offload a lot of our more intense elements, such as toolpath generation and the robot digital twin, to the cloud or to on-premises servers that are not in the cell.
So I guess just to summarize what we're doing in this case is we're looking at a semi-autonomous manufacturing process, and as Paul discussed some of the difficulties, in our particular manufacturing environment, we've got a lot of security protocols in place, and also the necessity for high quality assurance of parts. This creates a lot of problems and difficulties with the deployment of network-based services. However, through 5G Era and this project, and with the support of Paul, and HAL Robotics. What we have been able to do is, with the combination of the network-based microservices and the orchestration of the hardwares that we have deployed at our facility on site, we've been able to execute a potentially autonomous manufacturing process. And I guess one of the things about this particular use case is that it's a very small scale demonstration of MaaS, which is manufacturing as a service. And the idea we're trying to show with this is that this is a very small scale cell which could be replicated and also integrated into a much larger manufacturing as a service network, which could include kind of spokes such as the procurement supply chain, proper quality control, the original equipment manufacturers such as Rolls-Royce, Airbus, and also other processes that are required in the manufacturing stage, which could be upstream or downstream of our particular cell. So this diagram is kind of showing you what a manufacturing network could look like on a MaaS system. And I guess what I've tried to do is just show you that we are just one potential fabricator or worker within this to demonstrate how that could be used and deployed. So now I'll give you a quick update on what we've been doing in terms of our demonstration within our facility in Cambridge. So what we have here is what we're trying to do is some communication trials where we're running some very local tests and essentially making sure all the microservices that we've developed are engaging. So what we have here is the robot toolpath, also the dispensing of the paste. Currently we're working on the laser scanner, so we should be having that up online very soon as well. And we'll be running trials with our virtual and mixed reality headsets as well.
So from an operator perspective here as well, Alex's entire engagement is just to, in his mixed reality view, as I think this video will go on to show, I don't know if it's this one.
Next.
Oh, the next one. The video that we'll have on our stand later, his view is just he's seeing a list of all the jobs that are coming in, and he just selects a job based on the part ID or based on the job ID. He's not having to program anything about the robot, he's not having to design the toolpath while he's standing there, he's just selecting a job, hitting go, and the robot is extracting all that information from the information it has about the part. So when we see the robot come in and start applying the brazing paste around all the settings about the pressure of the paste, the geometry of the part, the speeds it's got to move at, all of that is being generated based on information that's contained within that job. So it separates the concerns of sort of an expert level design the job phase as a task, and the operator can just run that. So you could have multiple operators in distributed cells and one expert that's building these jobs for them.
So as Paul described there, what we have is two types of operators that we're trying to demonstrate. So we have an on-site operator, so what Paul described, which was someone physically present within the cell with a mixed reality headset, and they're able to interact with the robot cell through the microservices that we've deployed on 5G era middleware. So what this allows the operator to do is to engage with the robot through the logic flow diagram I showed earlier. So they will be able to confirm and accept the trajectory, the dispensing, and receive data from the laser scanner. So whether the part has passed or failed. And this is the type of the video is kind of showing you the type of visual that the operator will see whilst in this environment. The second environment we have is an off-site operator. So the idea is that this is a remote operator that could be present virtually through the virtual reality headset and could be located anywhere in the world in theory. However, as our use case, as I mentioned earlier, is a semi-autonomous process, we still require at the moment a physical operator on site. So just to do the loading and unloading of parts from the cell. But again, the off-site operator has the same ability as the on-site operator, where they can interact with the microservices through the virtual environment and directly engage with the robot, also receive data from the actual the setup that we've got. So receive furnace information, robot information, and also defect detection. So the role of the actual offsite operator is to be able to provide supervision of the process and have an overall arching view of what's happening in the cell. But also it could be a scenario where the on-site operator may require training and support, and the off-site operator, who could be located anywhere in the world, can provide this. And currently one thing we're working on is we're trying to update the visual that you're seeing in the virtual reality environment. So on the bottom is a very low resolution render of our manufacturing process, and we're currently updating that so the virtual environment looks as representative as the environment we have in Cambridge. So we're hoping to have that uploaded in the next couple of weeks, so this should look like a very nice environment. That's all from me.
Thank you very much. Thank you very much for your talk. Thank you very much for everyone. This is a summary of the use cases we are building up using 5G technology, using different kind of domain knowledge, combine them together to deliver things we can't achieve before. And we have a break, and we will resume in 20 minutes to 12, and we'll show you how we actually achieve them, because there's different kind of diversity over here, and we try to make the life of our developer easier. We build our middleware, we build connected robot platform to enable them. We'll explain how we do that. Thank you very much. That's our break, and we'll resume 20 minutes to 12.